Okay, so today we are going to actually talk a little bit about our first unit, which is scientific measurement. You'll notice that the PowerPoint and the notes on this are a little bit lengthy. There's a lot of things in here that are review and a lot of things in here that are new. So rather than waste all your time in the video doing the review stuff, I'm going to leave that up to you. So make sure you take a peek at the PowerPoint. One of the things you'll need to review, scientific notation. Another thing you'll need to review is just the basics of mass, volume, and temperature. So take the time to do that, and that will save us some time here. Because what we are going to do in this video is we're going to look at three different things. The first thing we're going to look at is something called accuracy and precision. Okay, accuracy and precision. Second thing that we are going to look at is percent error. And then the third thing we're going to look at is something called significant digits. Significant figures is another word, or more often than not, it's just called sig figs. These three things are probably very new to you, so that's what I want to spend our time on. So let's start with accuracy and precision. Okay, two very often misused words. Accuracy is very simply, how close are you to what you're aiming for? All right, now that's very simple terms, but that's just the easiest way to think about it. How close are you to what you are aiming for? So lots of times questions about these will use a dartboard or mini golf or something like that. So I'm going to draw us a little itty bitty dartboard here, and let's assume you're aiming for the bullseye. Okay, your first shot hits here. Well, first thing I want to say is, was that an accurate shot? Well, if I'm aiming for the bullseye, no, that was not an accurate shot. If it's me playing darts, that's an accurate shot. But if normal people, they're aiming for the bullseye, that is not an accurate shot. So accuracy, we can actually look at one measurement. Now let's say I have a couple more. I have another shot that goes right here, and another shot that goes right, well, we'll put them in here. Okay, are those accurate? No, you can kind of look at an average. In fact, let's say I have a fourth shot that lands right there, and I say, as a whole, are my shots accurate? The answer is still no. Okay, we're looking at an average, kind of where's the center point of all of them. On the flip side, let's say somebody hits one shot, two shots, three shots. That is accurate. All three right on the bullseye. So accuracy, how close are you to what you're aiming for? Precision is a little bit different. Precision is how well can your measurement be repeated? In other words, can you get the same thing over and over again? So let's go back to our dartboard again. Okay, let's say there's shot one, there's shot two, there's shot three. Okay, if we're talking about accuracy, are they accurate? No, they're not even close to the bullseye. But are they precise? Yes. These shots are all hitting right in the same spot. So even though I'm not hitting what I'm aiming for, I have a high level of precision because I'm hitting the same spot over and over again. Let's say here's one right here. One shot. Is that precise? I can't tell you that. You can't tell precision unless you have more than one because you're talking about can it be repeated. So if there was one, there was two, there was three, are those precise? Absolutely not. Okay, so we're looking at accuracy and precision together. If that shot one, that shot two, and that shot three, those are both accurate and precise. Okay, pretty simple. Second thing in today's video we want to talk about is percent error. One of the things that we talk about in chemistry is not necessarily are you right or are you wrong, but how wrong are you? Because there are very few times where you do a calculation and you will end up being 100% correct. Why? Because maybe your measurements weren't that good, but more likely than that, it's our equipment. The balances we have in our classroom only actually go to 2, maybe 3 decimal places. That really does limit you because there are more numbers out here that you're not seeing. Okay, so percent error, I'll give you your formula first, is the difference between what you got, okay, what you got and what you should have got, over what you should have got, and then of course times 100% to turn it into a percentage. Now, this top thing right here, the got minus should have got, is an absolute value, which means you don't have to worry about what order you put the numbers in. You can do the big one minus the little one minus the big one. It doesn't matter because you're taking the absolute value. It's always going to be a positive. So here's how this would work. Let's say I measured something and I got 72 milliliters. I should have gotten 76 milliliters, and I want to know what my percent error is. So when I plug it into my formula, okay, I'm going to have the absolute value of 76 minus 72. Again, I can write 72 minus 76. It doesn't matter. It's big minus little because it's an absolute value. I'm going to divide that by what I should have gotten, which is 76. And then I'm going to come over here and multiply it times 100% to make it a percentage. So again, the joys of the calculator, 76 minus 72 we know is 4, divided by 76, which is what we should have gotten, okay, times 100. That gives us a 5.26% error. I'm going to tell you right now, if you get that as a percent error, you are doing quite well. But that is percent error. This top portion up here, the difference between them, is often referred to simply as error. Okay, the difference between them is how wrong you are, but we want to use it as a percentage just so we can kind of have, I guess, a scope, we should say, so we can have a really good idea of exactly how off you are. All right, see, trucking right along. Now, third thing gets a little more challenging. It's the idea of sig figs. Significant figures or significant digits, I guarantee, are a new concept for you unless you have already taken physics. So what you need to know with sig figs is you need to know what in the world I'm talking about, okay? You need to know how to count how many sig figs there are in a measurement that I give you, and you need to be able to do rounding in calculations according to the rules of sig figs. Those are the three things we're going to talk about. Believe it or not, that's probably the hardest one, is what are they? So here's the idea of significant figures. Significant figures basically are all measured numbers plus one estimated. Yeah, I know, that makes absolutely no sense. So here's what that means. Here is my little generic ruler. Humor me. Okay, so let's say there is, in fact, I'm going to make my ruler even longer to make my life easier. I'm going to make it cover the whole thing. So let's say this is 1, 2, 3, 4, 5. Okay, nice generic ruler. And I want to know how long is this little red brick straw rectangular thingy. Okay, so significant figures tells me what kind of measurement I should be taking. So I want all the ones that I know, all the ones that are in the measurement, plus one that I'm estimating. So what do I know? I know this red thing is 3 long. I'm positive it is between 3 and 4. I can see that. Then I'm going to estimate one digit. So I'm going to say that's about a point, I don't know, we'll go 0.3. Okay, this is a measurement in significant figures. I have what I know plus one that I'm guessing. And it's only one that I'm guessing. Okay, according to the rules of significant figures, I cannot say that this is 3.25618. That's not correct. And this is something that's understood by all scientists. So every scientist knows, based on the measurement that is given, I know what kind of instrument you used. If you told me it was 3.25618, I know the only number you guessed on was 8. So that is one heck of a detailed ruler if you were doing that, because the 0.2, the 0.5, the 0.6, all of that, all those little teeny little lines have to be in there to make that possible. So that's the idea of significant figures. Okay? So let me give you another example. Let me draw myself another ruler here. Because so far you're like, okay, this is not that big of a deal. I can do this. Well, you know, it gets tricky. So there's 1, there's 2, 3, 4, 5, 6. Okay? So, again, I'm going to give you a little red rectangle, okay, that I'm going to have you measure. So So there's my little red rectangle. Okay, going right up to there. So now, remember, sig figs, I got to do all the ones I know plus 1 that I'm estimating. Okay, that's the deal. So, let's see, what would this one be? Well, I know it's 3, and then I'm estimating it's 0.0. Okay, right? 3.0. Okay, so now let's make it a better ruler. Okay, now if I put little 0.5s on here, okay, little 0.5s on all these guys. If I gave you a slightly shorter, let's say I give you this little blue guy, okay, you could still give me a good sig fig measurement. We'll kind of push that up and say, okay, that's probably, okay, we got all our little tenths in here, okay. Humor me, pretend they're all the same. So if we take that guy up, I know it's 2, I know it's 0.3, and then I'm going to guess it's 0.31. Okay? But what if I'm measuring my red guy on the ruler that has tenths on it? Okay? Ooh, sorry about that. So I'm measuring my red line on my ruler with tenths. Well, I still want to say it's 3.0. But if I say it's 3.0, it's telling me I know this and I'm guessing that. Well, I'm not guessing that. I know that. So now it has to become 3.00. This is the idea of significant figures. Okay? So zeros are kind of where this entire process gets tricky. So here are the rules for counting significant figures now that you kind of have a rough idea of what they are. We'll start with the simple one first. First of all, any non-zero is a significant figure. Okay? One of the things that your SOL is going to have you do is they're going to give you a number, 17. And they're going to say, how many significant figures is that? And you're going to say, well, that's 2 significant figures. 1, 2. Okay, so every non-zero always counts as a sig fig. Easy. So now we got to deal with the zeros. Number 2, if there are zeros that are in a sandwich, they count as significant figures. They are absolutely one of the known or the one estimated digits. So if I give you 203, that has 3 significant figures. Non-zero, non-zero, 0 in a sandwich. Okay, so any zero that's in a sandwich, 1.002, they're in a sandwich. That has 4 significant figures. So again, what sig figs are is they're talking about our measurement, but to count them, we're telling you kind of which ones were actually part of that measurement. So non-zeros count, zeros in a sandwich count. Now, rule number 3. What about zeros at the beginning or the end? Okay, if there is a decimal, okay, if you see a decimal, I don't care where a decimal is, if you see the decimal, okay, you are going to start at the first non-zero, and you're going to go all the way to the end, no matter if they're zeros, non-zeros, or what. Okay, so for example, if I give you 1.00300, all right, and I want to know how many significant figures are there. So what we're saying is which of these zeros are actually known and estimated digits. So, by my rule, start at the first non-zero. Well, there's my first non-zero. Go all the way to the end. So that's 1, 2, 3, 4, 5. That is 6 significant figures. Okay? Now, look at 0.0000320. All right? Now let's look at this rule. It says start at the first non-zero. Well, there's my first non-zero. So I've got to start there and go to the end, 1, 2, 3. So, if you see a decimal, start at the first non-zero, go to the end. Believe me, this takes practice. This usually doesn't really click to what you're doing and why you're doing it until sometimes halfway through the year. Sometimes it won't even be in this chemistry class. It'll be in a later chemistry class. Stick with this. If it's not making sense, learn the rules. Go through the motions. Try to keep making sense of it. Eventually it will click. All right, last rule, rule number 4. What if there is no decimal? If there is no decimal, then you very simply ignore any zeros at the end. Just the zeros at the end, because they're placeholders. Okay, so if I gave you the number 27,000. Okay, and I say, how many sig figs is that? Well, I don't see a decimal, so that means I can ignore these guys. Now, I can't turn 27,000 into 27. Okay, nobody wants that to happen to their bank account. But it means that this only has two significant figures. Okay, it means it tells you about the instrument in which it was measured. If I gave you 27 billion, okay, and I said, how many sig figs is that? Ignore the zeros at the end. How many sig figs is it? It is 2. Okay, so with counting sig figs, again, 4 rules. Non-zeros count, zeros in a sandwich count. If you see a decimal, start at the first non-zero, go to the end. If you don't see a decimal, ignore the zeros at the end. And be patient with yourself. The last thing you have to be able to do with sig figs is rounding. One of the number one questions that we get asked in chemistry classes and physics classes and math classes is, how many numbers do you want me to round this to? Sig figs actually gives you rules to answer that question, so you'll never have to ask again. Rule number 1 has to do with adding and subtracting. Obviously, I didn't make these rules because I would have one rule and one rule only, but that's the way it goes. So rule number 1 is about adding and subtracting. Rule number 2 is about multiplication and division. So you really do have to learn 2 separate rules. So let's start with the first one, okay? When you add and subtract, the rule for rounding is you round to the least number of decimal places, not sig figs, but the least number of decimal places as the numbers that you're using. So for example, if I did 2.7 plus 3.15, when I add that on my calculator, I get 5.85. But if I want to reflect the accuracy of these as measurements, that's when I have to decide how many digits I round to. So according to this rule, I'm going to do it based on the least number of decimal places. 2.7 has 1 decimal place. 3.15 has 2, so I'm going to round my answer to 1 decimal place. Now that does not mean cut off the 5 and make it 5.8. It means round. So because this is a 5, it becomes 5.9 as the correct answer. You will have SOL questions that ask you to round to the correct number of sig figs, and if you don't, you actually get the whole question wrong. Okay, so for adding and subtracting, it's based on decimal places. For multiplication and division, there is a separate rule. This is why you know I didn't make these rules. Okay, for multiplication and division, you are rounding this time based on counting sig figs. So multiplication, division are sig figs, okay? Adding and subtracting are decimals. So for example, if I did 3.5 times 4.23, put it in my handy dandy little calculator, I get 14.805. But again, if I want to reflect, okay, how these measurements right here were taken, that's when I have to go back to this rule. So 3.5 has 2 sig figs. 4.23 has 3 sig figs. That means I have to round my answer to the lowest number of sig figs, which is 2. So again, I have to round this to 2 sig figs. Okay, I can't just cut the end off. I have to round it. So when I round it to 2 sig figs, my answer is actually 15. This is something we'll practice a lot in class, okay? Use your practice problems, take advantage. There's videos out there on YouTube if this one's not working, but I'm telling you, this takes practice. You just have to do it. See you on the next one.